Okay, I'm a little bit confused, and but I want to warn you not to believe to 3/4 of the things that Francesco has said. Actually, he mentioned many of my students, but there are also other students he did not mention who didn't find very pleasant to work with me. I remember very, very good students many years ago, excellent students. And he finished his PhD, and I told him he wanted to get a postdoc position. And he said, well, actually, I've decided I want to change my career. I will become a psychologist. So probably it's not everything he said is completely true. Okay, and so this I added to the name of the conference a sentence, transire sum pectus mundoque potiri, which is written on the back of the field medals. It is attributed to Archimedes. It's not from Archimedes, actually. So it's that a translation, which is very overcome all limitation and master the world. Archimedes never wrote this sentence, but he wrote in his letters very many times praising the power of mathematics to solve problems. And well, since I'm a little bit moved, I will take a few seconds to tell a story that another great mathematician from Sicily, Professor Fichera, told us many years ago about Archimedes. Archimedes discovered the ratio between the circumference and the radius, and he wrote a friend in Alexandria to say that he had found a way of finding this ratio. And at that time, the letter took a couple of weeks to go from Syracuse to Alexandria. And meanwhile, he went through his proof and he found an error. So he wrote another letter to his friend in Alexandria, telling him, please erase that letter because I found an error. I will work deeper on it and I will try to give you a better demonstration of this ratio. So this is the way that people, mathematicians, face problems. They want to find not only a solution, but the solution, the one that can be proved without any doubt. Okay, so after that, I will go back to science, to mechanics. Scientists all work by Professor Greco. So you should have presented it. I will present it. I have added only some systematization, but I also want to thank the other co-authors, Professor Camarata, who's a professor of mechanical engineer, Catania, and almost Dr. Domenico Castello, who will present a second part of this talk on Thursday. Come ci va? Okay. So I'm going to talk about beams. So beams is a structural model. Structural model is defined by two pair, configuration space and a deformation operator. Both of them have implication in the sound model of beams. So the configuration space is a manifold. For beam, it's a manifold. There are many structural models where you have the manifold is a product of the linear space R3 and the rotation group. Yesterday we saw that Simon showed that we can use SE3 groups for modeling beams. The SE3 has been used for rigid bodies, but now we can model it with beams. So it's another manifold. And we need, in order to properly set the configuration, the deformation, to define the tangent configuration space where we with variation in velocity leave, and the tangent deformation operator. And we need a second variation in order to get the tangent stiffness metrics. So all these has implication in a robust model of beams. Okay, yeah. More? Okay. So, short, few words about the special orthogonal group. So, it's the Lie group of unique orthogonal matrices. The tangent space of the SO3 is the algebra of the skew symmetric matrices, and it's isomorphic to R3 through the actual vector. Very important operation that can be built on a Lie group are the exponential and the logarithm map. Exponential map is to go from the tangent space to the manifold. The logarithm is the inverse. So these are very important. They can be defined on any Lie group, and this is a simple expression. Is a power series development with the exponential map. And in SO3, this takes a very simple expression thanks to the fact that the skew symmetric metrics are repetitive, so the power, the skew symmetric matrix is equal to 2 power less. So here is the expression for the exponential map and the logarithm map in SO3. Okay. One important thing is that with the exponential map, it's very easy to define geodesic on the group. Geodesic in SO3 correspond to straight line in the tangent space. So if it takes the tangent line in the straight line, it maps into a geodesic. And this is very, very nice, and there would have consequences in the interpolation. Then we can differentiate the constraint that the R is an orthogonal matrix, and we get the structure of the Lie algebra, and define this way the left and right translation on an incremental compound operation that are commonly called spin in mechanics. They can be defined taking as a base point the rotation in the spatial and the material configuration. One is this the group language of the left or right translation. This doesn't work. This paper by McKenna is very nice, very nice summary of this theory. So if we have a path, evolution path of rotation, we can get the rotation in time t plus delta t, either by making the exponent of omega, which is the rotation plus the increment of rotation, or using the spin, left or right spin. These are 2 ways we can update rotation in the numerical models. Both have been used. And it is, if this works, okay. If we make the derivative of the exponential map, we get a relation between the increment of the spin and the increment of the rotation vector. This is usually called the Jacobian. It's a matrix. It's a matrix operator. And you can go from, it allows to give a correspondence between the increment of the rotation, which lives in the algebra, so in the tangent space to the density, to the spin, which lives in the tangent space to the rotation, to the aqua rotation. There are many many ways of deriving this Jacobian. Here there is sketched one, but anyway, you have to do the derivative of the exponential map. It can be generalized to any group. For instance, SC3, you have similar relations, of course, with different expression for the Jacobian. No. Okay. So in this way, we can obtain the tangent space, and velocity can also belong to the tangent space. So we have similar expression for the material and spatial velocity, very similar to the expression for this material and spatial space. So this is more or less this mathematical setting, which is very common, nothing new, nothing special, but it is important because it will be used. And that's what we want to reproduce. Mechanisms made by slender elements. Yesterday, Marco, he's not here, Jarko, showed a very nice experiment with the very slender phi beams. I'm curious to see if we can simulate this method. And so these are some systems that can be analyzed. Deployable structures like scissor structures. Rigid or non-semi-rigid pantographic mechanism, like in these orthopedic systems. The pantographs that have been developed by Francesco. This is the simplest one, but of course these are bistable or multi-stable elements called bigons that they are built flat, but then they give some torsion and they, for instability, change their shape. Okay. Deployable umbrellas, and Domenico Castello on Thursday will present all these results. So please stay there. Okay, now mechanisms, deployable antenna, and so on. So what we need to do to model all this, we need a very robust operator, a very robust model. We need to make a numerical model that is strain invariant, because we've seen that this deployable structure combines rigid body motion and deformation, so we have to exactly reproduce rigid body motion. There are very large deformation, even strains are usually not very large, but anyway, we need a locking-free formulation. And we need to be able to model assemblage of beams with different connection, pivots, maybe hook joints, and so on. So in this presentation, I will talk about Kosterá beams. We have also worked with Kirchhoff beams. So Kosterá beam we see it as a 1D Kosterá continuum. Is made by divided by a line. So the position of the line is we call P, and the orientation of the triad, an orthonormal triad on the cross section. Of course, the normal to the cross sections not coincide with the tangent to the beam. And so the configuration space is given by the position of the center line and the rotation of the cross section of the triad with respect to some reference system. The the operational difference in Euclidean space when we go on the group, on the rotation group, is given by the composition R transpose of R0. This is the analogous of the subtraction. We can build the classical deformation operator for the coastal beam using the same, idea of the coastal continuum. We build the gradient deformation, and then we make a non-polar decomposition using the micro-rotation, which is the orientation matrix for the triad. And doing this way, we can define the deformation, the strain, which is the difference of, this is the projection of the tangent to the beam over the the axis of the intrinsic triad. This is interesting because if you have a cross-rod beam and the section do like that, you do not have elongation. So the elongation is always a separation of the cross section. And doing something similar with the gradient of the rotation matrix and with the pullback on the collision configuration, we can define the Vrines tensor, and which is built with as an ingredient the Darboux vector. So actually the curvature, here, the difference between the pullback of the Darboux vector and the original configuration minus the Darboux vector of the reference configuration. So this is very classical. It's just a way of deriving it from. Okay. Then we need first variation in order to build equilibrium matrix, equilibrium equation. So this is the first variation of the strain, first variation of the curvature, the variation of the orientation of the orientation vector are done using the spin. So we need the spin, and so this is the expression of the first variation. And with the first variation, we can build equilibrium equation. These are the internal resultants. These are classical equilibrium equations for the coastal beam. These are written in the with the reference to the original configuration. This is T0 is the original length. But we need also the tangent equilibrium in order to build the stiffness matrix. So we have to the second variation of the internal energy. This is done by classical two ingredients, the material tangent operator and geometric tangent operator. In the geometric tangent operator, we have the second variation of the deformation, of the strain and of the curvature. And when we go to build the second variation, we have to make the variation of the spin. So we have the second variation of the spin, and that means we have to use the connection on the manifold. That disappears on a linear space, but in the manifold we need this to introduce the connection, and this is the Levi-Civita connection for the space SO3. This was originally found in this monumental work by Massimo. And we recognize the need to do the connection in order to get symmetrical action. Actually, what is nice is that what happens when you do it correctly, the action becomes symmetric, and what is the result is that the right way of doing it just eliminate the non-symmetric part of the action. So most people just, in some years ago, they just didn't find symmetric action, then symmetrized it, which is correct, actually. but it's not done in the right way, but at the end it comes out to be correct. To Kirchhoff line, the connection is slightly different, but can be generalized. Okay, these are the expression of the second variation. After applying the connection, they are, of course, symmetric. Now, that's for the model. Now we need to make numerical formulation. Okay, this is, and so we need to interpolate both the position. This is easy. This is linear space and rotation. Several ways have been proposed for interpolating the rotation. For instance, Cardona, Gerardin proposed to a polynomial interpolation of the rotation vector. This is not objective. Simo and then recently by Begovic proposed a polynomial interpolation of the spin. This is objective. I don't know if it is path independent. It is for 2 points, maybe not for more points. Who knows? Crisfield and Jelenic in 98, 99 proposed to use a spherical interpolation. Spherical interpolation, okay, in this work. Spherical interpolation is called SLERP, spherical linear interpolation. And it is the generalization of the interpolation in the Euclidean space on a manifold. Let's see. Okay, this is the idea. In a linear space, we interpolate between 2 points with just linearly. We want to do the same on a manifold. We have to do it along a geodesic. So the geodesic is expressed through the, as I told you, as an exponential map. So we can just interpolate the relative rotation and then make the exponential this relative rotation. We are interpolating along a geodesic on the manifold. So this is the basic idea, pretty well known in mathematics. Not only as it's been largely used in computer graphics. In computer graphics, they want to do very smooth animations, so they want to be able to interpolate correctly the movement. And for instance, this article, these 3 articles are were very well known in computer graphics, not much used in mechanics, and also in computer graphics they have also proposed higher order interpolations according to some rules. The problem is that in computer graphics they just want a smooth path, but we need also derivatives, interpolation of the variation, so we need something more. And up to now, what has been done has been 2-point interpolation. This was proposed by Crisfield, extensively used. And many people are trying to extend this spherical interpolation to more points. So it's using more unknowns in order to have the same order interpolation for the displacement and for the rotation. So what we've done.
Massimo, 10 minutes.
Okay, I finished. Let's move. What we've done is been to extend this interpolation to more control variables using the next, basically the Castro-Joe algorithm. The Castro-Joe algorithm is the algorithm used for interpolating Bézier polynomials. You substitute linear interpolation with spherical interpolation, and you get the spherical interpolation with more variables. It can be done also with B-splines using the Cox-Lebor algorithm, so it's very powerful. I'm not going into detail, just to show. So this is the idea. Start from a 2-point interpolation, between points 0, 1, 1, 2, 2, 3, then we interpolate between the interpolations on until the last level we get the complete interpolation using all the points of interpolation. No, finite. Then we have to do the same with the variation. So we have interpolated spin and the derivative, the turbo vector. That can be done. I'm not going into detail. Basically, the idea is to extend the Causal-Joule algorithm to these quantities. And what we got for this is for the spin realization of the interpolation that were given by Crisfield. Crisfield gave an interpolation of spin for the two-point interpolation. Spins are matrices. So these are the components of these two matrices, C1 and C2, that interpolate between two spins. And when we go to interpolating between more points, so in high-order interpolation, we have a system like this one, generalized the Bezier function multiplied by the control spins. These are built in a sequential way, following the Causal-Joule algorithm as a product of several, say, two-point interpolations. And this is what we got for the component of the matrices in the case of four-point interpolation. These are given some number. On the main diagonal are the interpolation, the term 1, 1, 2, 2, and 3, 3 of the interpolating matrices. They are the most important terms, very similar to the classical Bezier function, cubic Bezier function, are not, of course, identical. If you look at the numbers here, this is 1, this is 0.1. The out of diagonal terms are small. The more the path becomes straight, so because we have the rotation tends to become the identity, the more this function tends to become these three to the Bezier function, and the other go to 0. Okay, that can be done with also with the turbo vector and so on. And there are some expressions. They are very similar to what Simon presented yesterday. Okay, I don't skip all this part. Then the algorithm is quite simple, just a generalization of normal interpolation. And some example. First example is just to see if everything works. This is an objectivity test. It's a beam, 45 beam. It's rotated around the basis, 10 turns, no, 20 turns. 20 turns. And this plotted the energy for some degrees of interpolation, 0 at machine level. So it's okay. This is a path independent test. The other requirement is two force. First is applied one force and the other, and then the opposite, them both together. And the results are the same, whatever is the sequence of application. Here is also another path independent, another objectivity test is a beam is first deformed, is a pre-twisted beam formed with a force and then is rotated. So this is the energy associated with the rigid rotation, which is 0. So this is important because sometimes you have objectivity tests but did not work if they are applied to already deformed beams. And this is a classical example, is the ring. Okay, a ring that is rotated around one end. So the ring is rotated. Is after when you go do a complete turn, the ring becomes a smaller circle with a radius which is 1/3 the original one. Then you go on, the ring deploys again, and you can go on, and it opens and closes. And if the formulation is objective, you should recover always the same values of, of the internal forces. And this is with 10 turns, and the configuration repeat are always the same, whatever is the number of turns we get. So it's another way of testing the the objectivity of the formulation. When you have two complete turns, energy should be 0 because the ring has become again complete ring in the rest position. And at 2 pi, you have the maximum energy. It is after 10 turns, the energy is exactly the same. So this is basic. What I have presented is an extension of the Bezier interpolation, multiple point Bezier interpolation to structural systems. There are many things that can be done. The formulation can be extended to B-splines. This has been done. not presented, but it's already been done. In isogeometric analysis, this is very useful, except that in isogeometric analysis, we do not directly use B-splines on the interpolation, but what we do, we use Bezier function on a single element, which are easier to use, and then we project it on the B-spline using the Bezier extraction operator. But Bezier extraction operator is based on the fact that we can invert the operation of knot insertion. In a linear space, the operation is linear. We can invert it. In a manifold, the knot insertion is non-linear. Can it be inverted? No, but can be done something similar to Bezier extraction on a manifold? That's a nice question. Then extension to dynamics has been done. Formulation joint at the element level has been done. Dr. Castello will present it on Thursday. Kirchhoff's law rod also has been done. Dr. Castello will present it. And everything can be should be generalized to shells. And so some very interesting the extension to SC3. As Simon said, SC3 is intrinsically locking free. So it is, could be, yeah. But mathematics is the same, so we are very confident that it can be done. Another way of avoiding locking free is using mixed formulation. I did not present here. Domenico Castello will show the Kirchhoff law rod with mixed formulation is much more robust. Okay, so thank you. And again, thank you.